Hello everyone, I'm Haiyan Zhu from Chengdu University of Technology. Due to the current global circumstances, I am unable to attend this symposium in person and deeply regret this absence. Here, I sincerely invite all experts to visit Chengdu University of Technology. I look forward to having an in-depth, face-to-face communication next time. Now let's begin. The topic of my report is experimental investigation on multi-cluster temporary plug-in fracturing in a horizontal well, based on acoustic emission and distributed optical fiber monitoring. I will explain my report from these 5 parts. First, the background. China has the largest recoverable shale gas resource in the world, mainly concentrated in the Sichuan Basin, with recoverable resources reach 27.5 trillion cubic meters. The output in 2024 is expected to reach 24 billion cubic meters, accounting for over 95% of the national total. It is the main battlefield for shale gas exploration and deployment in China. After more than 10 years of scientific and technological research and development, China has formed a large-scale mean simulating technology of horizontal well complexion, plus multi-stage fracturing, plus multi-cluster perforation, plus sand carrying in sleep water, plus fracture monitoring, among which the number of single-stage clusters ranges from 3 to 17, and the cluster spacing is shortened to 5.7 to 16.4 meters. Under the condition of dense spacing, the strong phase interference between fractures leads to significant differences in the modification degree of each cluster of fractures. On-site optical fiber monitoring has found problems such as low fracture initiation efficiency of perforated clusters and the difficulty in uniform propagating of multiple clusters of fractures, which seriously restrict the efficient development of shale gas. Then temporary fracture opening fracturing technology can seal the perforated orifice that have already cracked, forcing the subsequent fracturing fluid to flow into other orifices and achieving the balanced expansion of multiple clusters of fractures. However, the on-site TPF forces mainly relies on engineering experience and lacks theoretical support, especially the position of the perforating coils that can form effective plug-in and re-crack has not been clearly defined, making it difficult to support the optimization of TPF parameters. To address those above issues, me and my integrated fracturing team for oil and gas geology and engineering, leveraging the State Key Laboratory of Oil and Gas Reservoir Geology and Exploitation, built a true triaxial experiment system integrating drilling, fracturing, and production under high temperature and high pressure conditions with multi-source monitoring. We conducted the physical simulations of multi-cluster fracture initiation in horizontal well and propagating during fracturing. These simulations were monitored using acoustic emissions and distributed fiber optic string techniques. These efforts aim to better understand fracture propagation and to provide theoretical support for promoting the balanced propagation of multiple fractures. Now, let me formally introduce myself. I'm Haiyan Zhu, come from Chengdu University of Technology. Currently, I serve as the Dean of the School of Energy at Chengdu University of Technology and have also joined ARMA's Future Leaders program. I also served as the chair of the selection committee for the ARMA's Distinguished Serve Award and mentor of the ARMA student chapter in Chengdu University of Technology. When Chengdu University of Technology was founded in 1956, it set up the Department of Petroleum Geological Exploration, offering the undergraduate major of Petroleum and Natural Gas Geological Exploration, which is now the College of Energy. In 1988, petroleum geology and exploration became one of the first natural key disciplines. On this basis, the State Key Laboratory of Oil and Gas Reservoir Geology and Exploration was established in 1990. These are the pictures of experts visited College of Energy and the gas field. Next, I will introduce our experimental apparatus. A true triaxial experiment system with multi-source monitoring for draining, fracturing, and production was built. It can be used for physical simulation experiments on horizontal wheel multi-cluster fracturing, fracture plugging, and supercritical CO2 fracturing. The sample size of the system is 400 multiplied by 400 multiplied by 400 millimeters, and the maximum confining pressure is 50 megapascal, and the maximum experimental temperature is 150, and the maximum injection pressure is 15 megapascal. We developed a 16-channel DS532C acoustic emission monitoring device. The continuous data transfer rate of the acoustic emission host is 262 megabytes per second, and the waveform data transfer rate is 192 megabytes per second. It is equipped with an RS2A ceramic probe and a gain-adjustable amplifier. An 8-channel T-shaped type distributed fiber optic shape monitoring analyzer was developed. The sensor is compatible with various fiber optic types and high-density weak reflection fiber printing strings. It has a lens composition function, enabling continued sensing measurements with the original reference file when the fiber optic lens changes due to break or repairs. Next, I will introduce our multi-cluster propagation experiment. An experimental method for multi-stage and multi-cluster fracturing propagating in horizontal wheels was developed. Experiments were conducted using a true triaxial experimental system, integrating drilling, fracturing, and production under high temperature and high pressure conditions. The AE monitoring systems was used to record the AE response characteristics during the fracture propagating process. The shear outcrops were proceeded into cubic samples. The distribution of bedding plans and natural fractures within each sample was described. At the center of each specimen, a horizontal wheel bore with a diameter of 15 millimeters and a depth of 360 millimeters was drilled along the horizontal plane. A multi-stages and multi-clusters injection wheel bore was independently designed and fabricated. Each fracturing stage corresponds to one injection line, and the stages are isolated by steel separators to achieve segmented injection. Annular steel sheets are welded on the outer surface of the wheel bore to stimulate perforation clusters. Each fracturing stage is equipped with a communication tube that runs through all perforation clusters to allow for epoxy resin filling in the long fraction segments. Using high-pressure injection lines and a 6-way valve, the 3 injection channels are connected to their corresponding intermediate ratios. Then the valve of corresponding intermediate ratio is opened while the valves of the other intermediate ratios are closed. The fracturing fluid is injected into the fracturing stage at a rate of 50 ml per minute through the injection system, thereby achieving the stimulation and sequential initiation and propagating of multiple fractures. Utilizing geometric scaling to design the experimental stage and cluster spacing. Using horizontal and vertical stress difference coefficients to design the experimental loading stresses. And employing lack of characteristics and dimensionless time parameters to design the fracturing fluid viscosity and ejection rate in order to achieve a similar fracture propagating regime. A single longitudinal fracture propagating through the upper part of the specimen is formed after fracturing, with local divergence induced by natural fractures. The fracturing fluid primarily gathers at the tongue of the horizontal wheel bore, while a small amount of fluid is observed near the heel. It is suggested that the longitudinal fracture fully propagated near the tongue of the horizontal wheel bore, resulting in a larger width compared to that at the heel. Fracturing fluids flow along the cementing interface and form a longitudinal fracture induced by natural fractures. After the first peak pressure is reached, the pressure drop is relatively small, and during the propagating phase, the pressure gradually increases with minor fluctuations. High-energy acoustic emission events occur along the wheel bore axis before the back-down pressure is reached, and during the injection phase, acoustic emission events are distributed along the wheel bore axis. with lower energy. HF1 is a transverse fracture and it crosses the N-wave to generate an orthogonal fracture network near the tongue of the horizontal variable. HF2 is also a transverse fracture and it divides at the N-wave after initiation to create a tape-like propagating geometry. In addition, the right wing of HF2 merges with HF1 at the N-wave, and in the lower part of the specimen, the fractures 1 and 2 extended in parallel. HF3 consists of an oblique fracture intersecting the horizontal variable and a transverse fracture, with the transverse fracture forcefully crossing the longitudinal fracture and propagating to the rock boundary. Multi-cluster fracture propagating. During the initiation phase, cluster 1 forms generating high-energy AE events at the variable axis. In the early stage of injection, the pressure fluctuates violently. Cluster 2 forms a transverse fracture, and cluster 3 forms a longitudinal fracture, with AE events widely distributed but of lower energy. In the later stage of injection, high-energy events occur on the left side of the variable axis, and the fracture from cluster 2 penetrates a lateral fracture. HF11 and HF12 are able to propagate in parallel after initiation, as well as HF31 and HF32. When the two clusters of fractures propagate to the bedding plane at the specimen top, one fracture is arrested at the bedding plane, while the other fracture penetrates the bedding plane and propagates to the rock boundary. HF11 and HF12 are communicated through the bedding plane, as well as HF31 and HF32, implying that the fracturing flowing among multiple clusters of fractures may occur by communicating with the weak planes, such as bedding planes and natural fractures. The hydraulic energy driving hydraulic fractures to propagate is gradually consumed as the fracture length increases, causing hydraulic fractures not to penetrate bedding planes in the vertical direction and training to be arrested by bedding planes. In comparison, multiple clusters of fractures tend to coalesce and form a dominated fracture. The simultaneous propagating of multiple clusters of fractures can open and connect multiple bedding planes. The pressure curve exhibits a multi-peak characteristic, with each pressure drop representing the initiation of a bedding plane fracture, and the pressure fluctuation rises, indicating that the injection phase is dominated by the seepage of fracturing fluid along the bedding planes. HF11 and HF12 can propagate in parallel in the near variable region. In the far field region, however, their propagating path in the length and height direction gradually coalesce. In stage 1, the lower part of the perforation clusters initiate one fracture. In stage 2, the upper part of the left perforation cluster does not initiate, while the lower part initiates 3 HFs, with the left fracture wider than the middle and the right fractures. In stage 3, only the upper part of the right perforation clusters initiates, while the left perforation cluster remains intact. The initiation of the clusters exhibits non-uniform and asymmetric characteristics. One approximately transverse HF and one longitudinal HF are created in fracturing stage 1. This transverse fracture intersects the variable axis at an angle of about 63. The longitudinal fracture grows along the variable and connects stage 2 and 3, leading into effective initiation in those two stages. In this case, the fracturing fluid lake off along the propagating path of HF1. However, the transverse and the longitudinal fractures do not penetrate the BP, but are arrested by it. The original geometry of HFs and BPs. After the initiation of stage 1, the pressure fluctuates violently with multiple high peaks. AE events are widely distributed across all projection planes, with high-energy AE events concentrated around the variable. The longitudinal fracture in stage 1 connects stage 2 and 3, resulting in the subsequent fracturing stages failing to achieve effective initiation pressure. HF is activated after injection, and the fracturing fluid enters the HF and flows along it, ultimately opening microfractures connecting to the NF and forming an inclined HF communicating with the NF. All three fracturing stages initiate to form transverse fractures. but the length and height propagating of those fractures created are suppressed, with fractures mainly distributed in the near wearable region. The interaction between multi-stage fractures and NFs. All three stages of fractures effectively initiate, but the distribution of AE events in the direction of fracture length was restricted. This indicated that the interaction of HFs with NFs activated the NF, thereby limiting the extension of fracture length. Under a stage spacing of 53 mm, HF2 divides toward HF1, with a deflection angle of one wing of 15 degrees. However, HF3 propagates in an approximately planar manner, which is similar to that of HF1. It seems that the stress interference has been significantly weakened the vicinity of HF3. Under a stage spacing of 33 mm, HF2 intersects with the horizontal wearable at a deflection angle of 21 degrees, with its left wing covering away from HF1 and its right wing coinciding with the previously created fracture. However, HF3 initiates and propagates near along the wearable axis, with its left wing dividing from the previously created fractures at an angle of 65 degrees, and the other wing intersects HF2. Compared to a stage spacing of 53 mm, the fracture propagating paths under a stage spacing of 33 mm are more significantly affected by stress interference, leading to intersections between subsequent and previously created fractures. Longitudinal fracture initiation and propagating. After the breakdown pressure, the pressure initially drops slightly and then rises slowly. High-energy AE events are concentrated at the initiation point, with numerous low-energy AE events distributed along the wearable axis. The clusters do not initiate at the same time, with the first peak pressure being relatively high. High-energy AE events occur near the first initiating perforation cluster, while low-energy AE events occur near the subsequently initiating clusters. Cross-lateral fractures. A significant drop in injection pressure occurs. Numerous low-energy AE events are initially generated, followed by a few high-energy AE events near the crossing points. Deflection along lateral fractures. Periodic fluctuations in injection pressure occur, with continuous low-energy AE events on the deflection side. Then I will introduce our temporary plug-in fracturing experiment, a multi-cluster temporary plug-in fracturing experimental method based on distributed optical fiber stream monitoring was developed. Experiments on fracture propagating of multi-cluster temporary plug-in fracturing in a horizontal wire were carried out using a large-scale true triaxial experimental system for integrated draining, fracturing, and production under high temperature and high pressure. The characteristics of fracture initiation and propagating of multiple clusters during the initial fracturing and the temporary plug-in fracturing stages were recorded by the optical fiber monitoring system. For optical fiber splicing, first strip the coating and cladding of the optical fiber to expose the fiber core. Then pre-clean the fiber end face with anhydrous ethanol. Finally, use an optical fiber contact to make the end face flat. After optical fiber splicing, use a heat shrink tube to provide protection for the spliced area. For calibration, first attach the spliced optical fiber to a 3D pointed U-shaped brackets. Then connect the jumper to the distributed optical fiber monitoring instrument. Apply stress to the starting point and end point of the U-shaped optical fiber respectively. Take the midpoint of the section that generates strain as the starting distance and ending distance of the measurement section. We design and fabricate a wearable with stimulated perforation clusters welded onto it. Wrap the wearable perforations with lab paper to prevent cement breakage. After inserting the wearable vertically into the cement mortar, ensure that the height of the middle perforation cluster is 200 mm. For optical fiber placement, first, lay a 10 cm thick layer of cement mortar. Then, place the U-shaped optical fiber brackets and the wearable vertically in the mortar. Lay 3 U-shaped optical fiber evenly in a direction parallel to the wearable, with a spacing of 10 cm between each optical fiber. The distance from the top of the fiber to the top of the rock sample and from the bottom of the fiber to the bottom of the work sample is 5 centimeters, and the distance from the optical fiber to the side surface of the work sample is 10 centimeters. Taking into account the equipment performance and simulatory criteria, the parameters are set as follows. Considering the field fracturing construction rates, the laboratory injection rates are calculated to be 20 to 15 mile per minute. Design a spiral-shaped optical fiber bracket constructor to verify whether the material of the bracket will induce the formation of weak planes, and at the same time test the matching degree between the fracture morphology obtained from the optical fiber monitoring and the actual fracture morphology to ensure that the monitoring system can accurately capture the dynamic evolution of fracture. The maximum radius of the helix R equals to 150 millimeters. The pitch P equals to 30 millimeters. And design a circular base with a reserved diameter D equals to 30 meters at the center of the helical structure. Design a built-in support structure to ensure that each helical layer remains complanar during the probing process and to prevent the structure from deforming. The preparation cluster is located at the depth of 200 millimeters, and one optical fiber bracket is set at a distance of 5 centimeters above and below the perforation cluster. The fracture pressure of the specimen was 10.18 megapascal. After the pressure application formed a vertical fracture. This fracture could pass through each spiral layer of the optical fiber brackets in sequence. The fracture did not divide along the support structure, indicating that the optical fiber brackets had a relatively small influence on the expansion path of the fracture. The position of the optical fiber string response is highly consistent with the intersection point of fracturing fracture and the optical fiber brackets. This indicates that the position of the optical fiber support in the rock sample has not undergone significant deviation, suggesting that the use of the bracket to lay the optical fiber path is feasible. For specimen number 1, the initial fracturing pressure was 11.63 megapascal, while the fracturing pressure during the TPF was 21.22 megapascal, with an increase of 82.46%. The initial fracturing of 3 clusters of perforations all resulted in the formation of transverse fractures. The fractures in the cluster 1 could fully expand, while the fractures in the second and third clusters did not expand sufficiently and had a smaller range. After the TPF, the fractures in the third cluster further expanded to the surface of the rock specimen. At a 3-cluster spacing, the initial fracturing resulted in 2 symmetrical strain bands. The central area had a lower strain, indicating that cluster 1 has fully fractured and formed symmetrical fractures. During the TPF stage, cluster 1 and 2 were successfully scaled, and the fractures of cluster 3 were further expanded. The strain generated by the fractures of cluster 1 decreased, while the strain generated by the fractures of cluster 3 gradually increased. Due to the small gap between the fractures, the strain bands of different clusters intersected. For specimen number 2, the initial fracturing pressure was 14.61 megapascal, while the fracture pressure during the TPF stage was 25.81 megapascal, with an increase of 76.66%. The initial fracturing of 3 clusters of perforations all resulted in the formation of transverse fractures. However, only the fractures in cluster 1 were able to fully expand, while the fractures in cluster 2 and 3 did not expand sufficiently and had a smaller range. After the TPF, the fractures in cluster 2 and 3 further extended to the surface of the rock specimen. At a median cluster spacing of 5 centimeters, the initial fracturing created 2 symmetrical strain bands. The middle area had a smaller strain, indicating that cluster 1 had fully fractured and formed symmetrical fractures. During the stage of TPF, the effective sealing of cluster 1 was achieved. Further, the fractures of cluster 2 and 3 were expanded. The fractures of cluster 2 first extended to the optical fiber, while those of cluster 3 extended to the optical fiber later. Due to the increase in cluster spacing. The interference effect of interfiber streets decreased, and thus no intersection of stream bands was observed. For specimen number 3, the initial fracturing pressure was 12.54 megapascal, while the fracturing pressure during the TPF was 20.25 megapascal, with an increase of 61.48%. The initial fracturing of those three clusters resulted in relatively low fluid injection volumes. Only cluster 1 expanded to a small area, while clusters 2 and 3 did not effectively fracture. After the TPF, clusters 2 and 3 fractured, and all three clusters' fractures extended to the surface of the rock sample. At a cluster spacing of 7 centimeters, the initial fracturing resulted in two symmetrical stream bands. The central area had a lower strain, indicating that cluster 1 has fully fractured and formed symmetrical fractures. During the TPF, clusters 2 and 3 were opened. The stream bands generated on the optical fiber waterfall diagram were wider than those of the previous two samples, indicating that the stress shadow effect between the fractures has decreased and the fracture morphology has become more straight. The small cluster spacing will intensify the stress shadow effect between adjacent fractures, hindering the expansion of the central fractures. On the other hand, the larger cluster spacing can weaken the stress interference, allowing the fractures to approach a more balanced expansion mode. For spacing number 4, the initial fracturing pressure was 8.59 megapascal, while the fracturing during the TPF was 45.7 megapascal, with an increase of over 400%. The initial fracturing only initiated fracture cluster 1, while the TPF initiated fracture cluster 4. Both of those formed transverse fractures. Additionally, a longitudinal fracture connecting cluster 1 to cluster 4 and parallel to the wearable direction was also formed. The final fracture pattern presented a H shape. At a pumping rate for 50 ml per minute, the initial fracturing process created two symmetrical stream bands. The middle area had a smaller strain, indicating that cluster 1 had fully cracked and formed symmetrical fractures. During the TPF, cluster 4 fractured. Cluster 2 and 3 did not crack effectively. The stream band at cluster 4 first increased and then decreased, while the stream band at cluster 1's fracture site increased, indicating that during the process of cluster 4 fracture gradually closing and cluster 1 fracture reopened. For specimen number 5, at a pumping rate of 13 mL per minute, the initial fracturing pressure was 6.61 megapascal. The TPA pressure was 49.16 megapascal, with an increase of over 600%. The initial fracturing only initiated the first fracture cluster. The temporary plug-in fracturing initiated the fourth fracture cluster, forming transverse fractures. At the same time, the third fracture cluster formed a longitudinal fracture parallel to the wellbore. This longitudinal fracture turned direction when it extended towards the wellhead and reached the second fracture cluster. During the initial fracturing process, the strain changes throughout the entire fiber area while relatively small, with only slight strains occurring at the beginning and the end of the fiber. This indicates that the fracture that initiated the fracturing had a relatively small extension ridge and did not extend to the fiber itself. It is speculated that only the first cluster formed a cross-cutting fracture with insufficient extension. During the TPF, cluster 4 fractured. However, only one end of the fracture extended to the optical fiber, while the extension ridge of the other end was smaller. This indicates that the fracture in cluster 4 is an asymmetric extension fracture, with only one side of the fracture extending fully. For specimen number 6, at a pumping rate of 20 ml per minute, the initial fracturing pressure was 8.09 megapascal. The TPA pressure was 13.77 megapascal with an increase of 17.2%. The first fracture initiation, cluster 1, on the low flow rate. the temporary plug fibers fail to effectively seal the fractures of cluster 1, but they caused the fractures of cluster 1 to change direction. The fractures extended from cluster 1 towards the wellhead, forming a longitudinal fracture parallel to the wellbore. The initial fracturing resulted in stream bands at the beginning and end of the U-shaped support, indicating that perforation cluster 1 initiated the fracture, forming transverse fractures perpendicular to the wellbore. During the TPF, the strain zone appears at the location where the initial fracturing caused strain. This indicates that the TPF failed to open new perforation clusters, but instead continued the expansion of cluster 1 fractures. Under low pumping rate conditions, it is difficult to form an effective plugin for the opened perforation clusters. However, with high injection speed, the fracturing fluid can enhance its carrying capacity for the temporary sealing edge fibers, making it easier to form an effective plugin for the opened perforation clusters. For specimen number 7, the initial fracturing pressure was 15.9 megapascal. During the TPF stage, it rose to the fracture pressure of 28.68 megapascal with an increase of 18.38%. During the initial fracturing process, fluid was injected into the first, second, fourth, and fifth clusters of perforations. However, the expansion of range of the fractures in the fourth cluster was relatively small. After the TPF, the fractures in clusters 1 and 2 further extended to the surface of the rock sample. Due to the relatively small stress difference, the fractures all slightly divided towards the wellhead direction. The initial fracturing of U-shaped brackets at the front end resulted in a stream band, indicating the initiation of the first clusters of perforations. However, no stream band appeared at the rear end, suggesting that the cluster 1 expanded on the one side. During the TPF stage, the fiber waterfall diagram relieved multiple asymptotic stream bands, indicating that the TPF process created multiple new fractures. Due to the stress interference between the fractures, the stream bands generated by each fracture intersected with each other. For specimen number 8, initial fracturing pressure was 6.81 megapascal, resulting in 2 pressure peaks. The TPF pressure was 13.08 megapascal, with an increase of 92.07%. The initial fracturing opened the first and fifth clusters of perforations, and the fractures were relatively straight. The TPF opened the second clusters of perforations in the rock sample. All 3 fractures were transferred cuts perpendicular to the wellbore, and the 3 clusters of fractures expanded in a relatively balanced manner. For specimen number 9, the initial fracturing pressure was 5.25 megapascal. The TPF pressure first reached 4.92 megapascal and then gradually increased. It is speculated that TPF particles have clouded the wellbore. The pumping was stopped when the pressure reached 14.3 megapascal. Cluster 1 developed a transverse fracture perpendicular to the wellbore. Due to the deposition of temporary sealing particles inside the wellbore, failed to achieve an effective plugging. During the initial fracturing, a stream band appeared at the front of the U-shaped brackets, while a smaller strait was observed at the rear end, indicating that the first fracturing cluster 1 had initiated fracture propagating, and the expansion range of the left wing fracture was larger than that of the right wing. During the TPF stage, no new stream bands appeared on the fiber waterfall diagram, which was in the same position as that of the stream bands in the initial fracturing stage. This indicates that the temporary plugin failed to create new fractures, and the fractures flowed along the cluster 1 fractures. Under conditions of low stress differences, it is more likely for the unopened perforation clusters to fracture. The fractures are more likely to expand towards both sides as the stress difference increases. The difficulty of initiating new fractures by temporary plugging increases. The number of initiated new fractures decreases, and the fracture expansion from its many single cross-cutting fractures. Finally, here are the ongoing novel experiments. The first one is multi-well 3-dimensional fracturing physical simulation experiment. Prepare a specimen and drill 5 horizontal wells with scheduled distribution, which are arranged in upper, middle, and lower 3 layers, combined with the AE distributed optical fiber strain monitoring system and strain gauge analysis system. Monitor the fracture stress conduction path during multi-well fracturing and reveal the interior stress interference mechanism and the connected morphology of interior fractures. The second is laboratory experiment on physical modeling of hydraulic fracturing for infill wells considering non-uniform pressure distribution. Fabricate a square plate-shaped specimen with dimensions, preset natural factories. Drill 3 well bores in the plate-shaped specimen. Saturate the specimen with fluid and maintain a contact fluid pressure around the specimen. Inject fluid into 2 of the well bores to simulate the fracture propagation process of pre-existing wells. Subsequently, extract fluid from those 2 well bores to mimic the production freeze of the pre-existing wells, thereby creating an artificially non-uniform pressure distribution. Finally, inject the fluid into the remaining well bore to stimulate the hydraulic fracturing process of an infill well. The third is true traxel experiment on fault slip induced by fracturing stress. Conduct physical simulation of stress transfer during fracturing using a large true traxel physical simulation system. The rock specimen is 200 mm cubed. Perforation eyes are located near the fault plane to allow fracturing fluid to enter the fault and activate its slip. 8 strain gauges are arranged on the fault surface. Strain gauges are used to monitor the slip. Characteristics of the fault plane. Meanwhile, a high-frequency acoustic probe is used to monitor fracturing AE signals, and a low-frequency acoustic probe is used to monitor slip signals. Experimental findings indicate that increasing the fluid weight or decreasing the minimal horizontal stress leads to a gradual shift in the stress change pattern before fault activation, from a stress surge to a stress accumulation mode. During multiple fault activations, the in situ stress is the key factor influencing the relative magnitude of sequential slips. When artificial fractures form, fluid flows into the fault with reduced volume, lowering fault activation. If no artificial fractures form, fluid flows into the fault through pores. This dominant flow path increases the fluid volume in the fault, enhancing fault activation. That's all. Thanks for listening.